Okay, so we were here at the Moore's absorbing boundary condition. So this would be actually extension of what we have done for absorbing boundary conditions. So this is actually one of the popular boundary condition, and the most popular one is usually perfectly matched layer. We'll see later on. But this also works well, quite well. Moore's absorbing boundary condition or boundary condition. So let's say you have a TM wave, and consider that it has only Ez component. So this is the wave equation: del square by del x square plus del square by del y square minus 1 by b phase square del square by del t square Ez. Ez is the field you want to calculate. So now you can just combine these two terms here, just separate out this term here, del square by del s square, and you combine the second and third term here. So now you can also see, this looks like a square minus b square kind of thing. So this looks like a square minus b square kind of thing. So you can write a plus b and a minus b. So that's what Moore's approximation does. This operator here operating on Ez, you actually consider this as something like a square minus b square, then a minus b plus a plus b. So this becomes del by del x plus 1 square root of 1 by b phase square del square by del t square minus del square by del y square. Only the second term, only sign change is there. You have a minus sign here. So now this operator here, I will call it psi plus, and this operator here, I will call it psi minus. Then I can write this wave equation in a very compact form. Psi plus psi minus Ez is equal to 0, where psi plus is del by del x plus square root of 1 by b phase square del square by del t square minus del square by del y square. Psi minus is this. Psi plus is this, psi minus is this. Okay, so actually Moore's boundary conditions make an approximation of this expression of the operator psi plus and psi minus. This psi plus you can express as del by del x plus 1 by b phase del by del t square root of 1 minus s square, where s is defined as b phase del by del y divided by del t. You can just simplify it like this. Just define s as like this. You can simplify, write the exact expression of psi plus like this. So now from here you can see that there is a 1 by square root of 1 minus s square here. We can use Taylor series expansion of that. Square root of 1 minus s square is 1 minus s square by 2 minus s to the power 4 by 8 minus s to the power 6 by 16 minus and so on. But we would be interested only in first and second terms. So if I just take first term, the simplest approximation of square root of 1 minus s square is equal to 1, then we call this as first order Moore's boundary condition. So this is first order Moore's boundary condition, where you just take the Taylor series expansion of square root of 1 minus s square as simply 1. In that case, your psi plus will simply become del by del x 1 by b phase del by del t of Ez. So now you just take square root of 1 minus s square as 1. So psi plus Ez will become del by del x Ez plus b phase 1 by b phase del Ez by del t is equal to 0. Psi minus will simply become minus sign here. So you have psi plus and psi minus. Your wave equation is psi plus into psi minus into Ez is equal to 0. Now you can do a finite difference approximation of that. So what do you have? You have del Ez by del t term here, del Ez by del x term here. How do you do finite difference approximation of that? So if you want to do finite difference approximation of this del Ez by del t, you can simply do it Ez at n plus 1 minus Ez at n divided by delta t. You calculate Ez at 3 by 2 here. And right hand side del Ez by del x, so del Ez at 2 minus Ez at 2 minus Ez at 1 divided by delta x. and you calculate this at time instead of n plus half, n plus half. This is half 3 by 2, 3 by 2. This is n plus half, n plus half. But if you consider 1D case, so I want to find only Ez, then it's a 1D case. In the 1D case, your electric field as calculated in integer time step and space step. So I do not have the values of electric field and at half integer time and space step. So if I want to find that unknown, which is calculated at, let's say 3 by 2 is half space step, n plus half is half time step. So I don't have these values when I consider 1D Fdtd. So then what do? I just average it. For example, if I want to find Ez2 at n plus half, then I just find Ez2 at n plus 1 and Ez2 at n. Then average it. Or let's say if I want to find Ez1 at n plus half, I just take Ez1, n plus 1 and Ez1 at n. Everything is integer steps now, and you just take the average of it. For example, if I want to find Ez at 3 by 2, I just find Ez at 1 and Ez at 2. Here also I want to find Ez at 3 by 2, I just find Ez at 1 and Ez. Just take average, then I can find it. So finally you can simplify it, take those terms where in the left side and right side, and you can see there's a constant term here, 2 delta t and 2 delta x. So delta t b faced by delta x. You rearrange the term. If you want to find Ez at 1 at n plus 1, this is the latest one, Ez at 1 at n plus 1, then you can simplify this expression. It turns out to be this term here to Ez at 2 at n minus 1 minus this term here, Ez at 2 n plus 1 plus 1 minus this term here, Ez at 1 n. Okay, so you can further simplify it. You have a Ez at n plus Ez at 1 n plus 1. You can take this to the right hand side, then simplify it. It can be expressed as Ez at 2n. Then this ratio here is Ez at 2n plus 1 minus Ez at 1n. So that's how you can update the Moore's absorbing boundary condition at the edges, not at every point, only at the edges. At the boundary, you can do this kind of update equation. So you write the Fdtd equation. Whenever it reaches the boundary, the update equation will be different. So boundary will have a different update equation. All other places, same update equation. If you apply the CFL condition, current stability criteria condition, Bp delta t by delta x is equal to 1, then simply you get Ez at 1 n plus 1 is equal to Ez at 2n. Similarly, you can also do it for the rightmost. This was for the leftmost. 1, 2 is for the leftmost case. Rightmost, then you'll have Ez at n plus 1 Imax is equal to Ez at n Imax minus 1. This term is same equation, except that this term here should be at Imax and Imax minus 1. So it is 1 and 2. Rightmost would be Imax and Imax minus 1. So if you use this update equation, you can absorb the wave at the boundary. So that was the first order Moore's boundary condition, and it doesn't give you very accurate boundary condition. Some of the waves reflects back. So if you want to improve the accuracy, you need to take the higher order terms in the Taylor series expansion. You can have second order, third order, fourth order. The only thing is that if you go on taking the higher order terms, your computational complexity is going to increase. Accuracy is definitely going to improve. And along with that, your computational complexity is going to increase. So if I take the second term, we call it second order Moore's boundary condition, 1 minus s squared by 2. So psi plus is del by del x 1 by v phase, del by del t 1 minus s squared. What was s? You can just substitute it here. Then finally, you can simplify it. Psi plus would be del by del x plus 1 by v phase del by del t minus. You can further simplify it. The final expression psi plus Ez would become del square Ez by del x del tau plus 1 by v phase del square Ez by del t square minus v phase by 2 del square Ez by del y square is equal to 0. Similarly, psi minus, then you just have a simple sign change for the second term here. So this will become minus, this will become plus. Sign change for the second and third term. Same expression, only sign change for the second and third term for psi plus and psi minus. How do I do the discretization in Fdtd? So how do I do the discretization? So that can be See, you have terms like del square Ez by del x del t, and you also have terms like del square Ez by del t square, del square Ez by del y square. These terms are there. So let us try to do discretization for del square Ez by del x del t first. At nth time instant at and 3 by 2j. This for 3 by 2j, then how do you do it? You have a partial derivative with respect to time and partial derivative with respect to x. Two derivatives. Let's say I want to do the partial derivative with respect to time first. Then I want to do partial derivative with respect to time first. Then it will become 1 by delta t del Ez by del Ez by del x at 3 by 2j, same location. Only the time is n plus 1, n minus 1, 1 by 2 delta t. Because we are doing this derivative over 2 time intervals, that is because you will see that it is easier for us later on because we have many double differentiation here. So we'll have to do it so that it should be similar expression with that of the double differentiation. So 1 by 2 delta t del Ez at n plus 1 and del Ez at n minus 1 at same location, 3 by 2j, 3 by 2j. Okay, so 1 by 2 delta t, and you can again do the partial derivative with respect to x, del Ez by del x. Del Ez by del x would be Ez at 2j and Ez at 1j, n plus 1, same time instant, n plus 1, n plus 1. Same time instant, n plus 1, n minus 1, n minus 1. If you want to do partial derivative of del Ez at 3 by 2j, then you just find out Ez at 2, comma j, 1, comma j divided by delta s. This is the partial derivative with respect to x, partial derivative with respect to x. Similarly, you can also do partial derivative with respect to y, double derivative here at 3 by 2j and n. So now, this, you can do it like this, half of, see, I want to do it at 2j and 1j, so half of 3 by 2, I want to get rid of this 3 by 2, then I actually take the average of half del square Ez by del y square at 2j, and del square Ez by del y square at 1j. You take the average of that, then I get the Ez at this derivative at the location 3 by 2j, just like we have done in the previous case. So now these are double derivatives. Double derivative, you know how to do double derivatives. Double derivatives, then how do you do it? Ez at 2 comma j plus 1. We are doing partial derivative with respect to y. Running index for y is j here. So here what you see is j here, Ez at j plus 1, Ez at j minus 1. This is because it's a double derivative. That's why even time also we have done it for n plus 1 and n minus 1 because it's for 2 time intervals. When you do partial derivative with respect to y, double differentiation, you have to do it over 2 intervals, j plus 1, j and j minus 1. That's why I have done time derivative over the 2 intervals. So this is a double differentiation, Ez at j plus 1 minus twice Ez at j plus Ez at j minus 1 divided by delta y square. It's a double differentiation. Time is same, and at time is 10, and at time is 10. Similarly, you can also do the double derivative with respect to y at nth time is 10. For 1j, then you have to go over two intervals j plus 1, j and j minus 1. 1 comma j plus 1, 1 comma j, 1 minus 1 j minus 1 divided with delta y. You can also do time derivative with respect to time double derivative of Ez at nth time instant 3 by 2j. So I want to make it over integer space step, so I just change it to average of 2 comma j and 1 comma j. Half of that I will get this value here. So we can do the double derivative with respect to time, then n plus 1 n and n minus 1, n plus 1 n and n minus 1. Space location is fixed 2 comma j here, 1 comma j here, divided by delta t square. So you can do the discretization now. So the final expression for the update equation looks like something like this: Ez at 1 plus 1 comma j at n plus 1 is equal to minus Ez at 2 comma j n minus 1. We just rearrange all the terms. That's it. And just put the latest one on the left hand side. So that's how you do the second order Moore's absorbing boundary condition. We have done first order also, second order also. Okay, so we have time. It's 12:35 now, so we can go to the 3D case. So now for the 3D Fdtd, we have two Maxwell curl equations. So we'll have three equations for here, three equations for here. We'll have 6 equations total. We have to solve all of the equations, so it's very lengthy. But anyway, we have already understood what is 1D case, 2D case. We're coming to 3D, so it should not be difficult for you now. So this is the master diagram for the 3D Fdtd. We have already discussed about the master diagram for 1D Fdtd. It was for the leapfrog manner. Then we have discussed it about the 2D Fdtd. It was electric field was at the center and magnetic field was circulating the electric field. And similarly, this is the master diagram for the 3D Fdtd. This is called use Fdtd grid. So actually, this diagram is given by Yees. So, and it's very famous. So if you look at this diagram from the paper, you may not understand it unless someone tells you what's going on here. So look, so many arrows. There are 6 arrows here. Every arrow is actually giving you direction for electric field and magnetic field. You can see electric field EX here, EY here, EZ here. Similarly, IX, IY, IZ here. There are 6 arrows. 3 for electric field and 3 for magnetic field. But the position of arrows is very important here. This diagram should be there in your mind when you actually write your Fdtd code or Fdtd update equation. So let us try to understand what is this diagram. So first look at EX. EX obviously is a vector component electric field along the X component of the electric field along X-axis. So this is directed along the X-axis. This is your X-axis direction. EY is directed along the Y-axis. EZ is directed along the Z-axis. Let us first try to understand what is EX, EY, and EZ. Where is it placed in the cube? This cube is one unit cell. One unit cell for Fdtd. So now, where is the location of electric field and magnetic field for one unit cell for Fdtd for any general cube? So this diagram is applicable for any case. It's a very general diagram here. So EX is directed along the X-axis, and what do you see? It is placed at the edge. This edge is along the X-axis. This edge is along the X-axis. Along the X-axis, along the edge, along the X-axis, it is placed at the center. And similarly, this is the Y-axis. Edge along the edge of the cube along the Y-axis, you're placing it at the center. And here, you're placing EZ along the S along the Z-axis, and it's at the center. Just remember that at the center of every edges along X-axis, Y-axis, and Z-axis, we are placing EX, EY, EZ. And how about this IX? IX is placed at the face of the cube. So this is Z, this is Y. So if you have IX here, what are remaining variables? Y and Z. So this is a face in the YZ plane, and you're placing IX at the center of that. Similarly, IZ is placed at the face. What are remaining variables? X and Y. X, Y, face at the center of that. Similarly, XY is what are remaining variables? X and Z. So it's placed in the center of the face of the XZ. Okay, so let us go back to the update equation. So there are a few things you need to remember here. Unlike 1D and 2D Fdtd cases, electric fields are calculated in integer time steps, and magnetic fields at half integer time steps. When you write the update equation, all the electric field will have integer time steps. All the magnetic field will have half integer time steps. So you need to just remember this. You can do it other way around, but it has been done like that in the literature conventionally. So if you change it, then you might actually get lost. You might get confused. You may not be able to write the Fdtd update equation properly. So this is a conventional way. Just follow the convention so that you don't get lost. So electric fields are calculated at the integer time steps, and magnetic fields are calculated at the half integer time steps. And electric fields are placed at the midpoints of corresponding edges. EX is placed at the midpoint of edges oriented along the X direction. That I have already told you in the previous master diagram. E is Fdtd cube. So now what is that means? Ex is placed at the midpoint of edges oriented along the x-axis. That means Ex is on the half grid in x. So Ex is on the half grid means Ex will have space step along the x-axis would be half integer steps. But along the y and z axis, it's in the integer steps. So it will have integer space step for y and z and half integer space step for x. Okay, similarly, you can do it for EY and EZ. Let's say magnetic fields components, how magnetic fields components are placed on that master diagram, E is cube, placed at the center of faces of the cubes and oriented normal to the faces. For example, ICX was placed in the face of YZ plane, center of the face in the YZ plane. So what does that mean in terms of Fdtd update equation? That means ICX is on the integer grid in X and on the half integer grid in YZ. Since it's at the center, it would be in the half integer grids. So this point here, this is integer. This point here, this is integer. This point here, all these are integer. But if you are at the center, then you are in the half integer grids. So that's what you need to remember. So let us write down the Fdtd update equation for the first Maxwell equations. First component of the Maxwell equations, dou Ex by dou T is equal to 1 by epsilon R epsilon 0 dou Iz by dou Y minus dou Iy by dou Z. If you know only this, then you know all other remaining 5 equations. So just pay attention when you write this first equation. Once you know this, you can write all other remaining equations easily. So first thing first. Remember, Ex was placed at the center of the edges along the x-axis. So we have 3 running variables for Ex. For the x-axis is P, another y-axis Q, and R for the z-axis. So running index for the x-axis is P. So P will become P plus half because Ex is placed at the center of the edges along the x-axis. So Ex will have P plus half QR and Ex will have P plus half QR. Now we are doing partial derivative with respect to time. So it will be n plus 1 to n. Electric field was calculated at the integer time steps and magnetic field was calculated at the half integer time steps. So electric field will have only integer here. So we can have n plus 1 n divided by delta t. Left side is clear. So let us look at the right hand side. Right hand side, look at the first term here, del by del y of Iz. First thing first, Iz is a magnetic field. So you calculate the magnetic field in the half integer time steps. So it will be n plus half here. We have taken n plus 1 and n plus n here. In between that, we have n plus half. So n plus half, n plus half. Time is clear. How about the space? Iz, then it is in the phase, what are the remaining variable? XY plane, in the XY plane. So that means X and Y will have half integer grids and Z will have integer grids. So that means X and Y will have half integer grid means P plus half, Q plus half, P plus half, Q minus half. Because we are doing partial derivative with respect to Y, so Q plus half, Q minus half. And it is at the center of the XY plane. So Z anyway will be integer grid here, so R here. Similarly, you can write down the Fdtd discretization of del Iy by del Z here. It's a partial derivative with respect to Z. And it's a Iy. Iy is a magnetic field. So what are remaining variable for Iy? Y here. So X and Z. So this is in the center of the face of the cube in the XZ plane. So XZ plane. Then XZ plane means X and Z will be half integer grids. Y will be integer grids. So Y is Q. Running index for Y is Q. So Q here. So this P plus half, R plus half. Partial derivative with respect to Z, so R minus half here. So that's how you write the discretization version of the Maxwell equation here. Once you know this, you can do the other one very similar. For example, you want to do del Ey by del T. So electric field is calculated at the integer time step. So n plus 1 n here EY is at the center along the y-axis, as along the center of the y-axis. So EY, which is the running variable for y, q plus half, q plus half. Others will be integer PR, PR. Right hand side, del is x by del z is a magnetic field. It's at the center of the face of the this x here, so yz plane. So yz plane will be half integer grids and y will be integer grids. Y is which one? So this is x. X will be integer grid and y and z will be half integer grid because x is in the center of the face of the cube in the yz plane. So pq plus half r plus half, partial derivative respect to z, so pq plus half r minus half. So now we have taken n plus 1 n here, in between you have n plus half, so n plus half here. Similarly iz also n plus half, n plus half. Iz is in the face of the cube in the xy plane, so x and y will be half integer grids, z will be integer grids. So r is integer grids, r is the corresponding variable for z, but x and y will be half integer grids, p plus half, q plus half, partial derivative with respect to x. So this will be delta x here. So this will be delta x here. There is a typo here. P plus half, q plus half, p minus half, q plus half. I will do one more, and then you can do the remaining thing. Okay, so del Ez by del T. Ez is at the center, midpoint of the edges along the z-axis. Running index for z is r, so r plus half, r plus half. Others will be integer, pq, pq. Partial derivative with respect to time delta t. So n plus 1 and n, because electric field is calculated at the integer times this. Look at the right hand side del is y by del x. Partial derivative with respect to x and is is y. So this is at the center of the face of the cube in the xz. So x and z will be half integer grid. So x is running index is p plus half, p minus half, r plus half, r plus half. You are doing partial derivative with respect to delta x, so this will be p minus half. Similarly, del is x by del y. Time is at the half integer time step, n plus half here. It's in between n plus 1 and n. And x means is in the center of the face along yz plane. So y and z would be half integer grid. P plus half, q plus half, r plus half. Y and z means q and r, q plus half, r plus half, q minus half, r plus half. Partial derivative with respect to y, so you should have q minus half here divided by delta y. And x will be integer here, p here, p here. So that's how you do the discretization of the Fdtd equation for 3D case. I'll one up here, we can discuss.